Previous videos in this series have discussed statistical parameters like the mean or the median or the standard deviation that we can use to describe data. This video instead covers methods that are used to determine uncertainty in those parameters, especially uncertainty in our estimate of the mean. So this question arises because we're using samples to estimate characteristics of the broader population. So for example, we use the sample mean, x bar, to estimate the true but unknown population mean, or mu. So how can we quantify the uncertainty on our sample mean? Is it a really precise estimate of the population mean, or is it an uncertain estimate of the population mean? So to illustrate this, let's first imagine that if we want to estimate uncertainty, let's say that instead of just having one sample, we actually have many samples taken independently from the population. So we have our population and we take a sample and we calculate the mean of that, and we take another sample and we calculate the mean of that sample. So each of those samples has its own mean value, and those sample means will be distributed around the true population mean, which in this case is 3. So for example, the mean of sample 1 might be 2.81, let's say. The second sample might have a mean of 2.94, the third one 3.13, and so on for all of the many samples taken from the population. So the histogram here, the green bars, shows you the distribution of those sample means. So the distribution of sample means around the true population mean is an example of something called a sampling distribution. A sampling distribution is the distribution of a calculated parameter, like the mean. It's not the distribution of raw data. It's not the measurements that you made. It's parameters. Like it's a whole bunch of different means if you had done many random samples from the population. So you'll see sampling distributions in a few weeks when we discuss resampling methods later in the quarter. But for our purposes here, the standard deviation of this sampling distribution, the standard deviation of all of the sample means, if we took a whole bunch of them from our population, defines this parameter called the standard error, or the standard error of the mean. So the standard error is this measure of uncertainty in the mean. So, the sampling distribution is nice and all, but of course you don't actually have many independent samples from the population. You just have one sample usually. Fortunately, the standard error of the mean can be estimated from the raw data itself. You just use this formula, standard deviation divided by the square root of sample size. And I won't get into the math of where this formula comes from, but it is sort of intuitive, and it does make sense intuitively at least. If the standard deviation is larger, that means that the raw data is much more variable. And if the raw data is more variable, then its mean is probably not as good of an estimate of the population mean. Likewise, the sample mean will be a more reliable estimate of the population mean when you have more data points. When the sample size n is larger, the standard error will then be smaller. So just a reminder, standard error measures how accurately the sample mean estimates the true population mean. Standard deviation, which you've heard about before, is a measure of the scatter or the variability of sample data around the sample mean itself. So even though they both have standard and they can be confusing sometimes, they're very different parameters. We use one, the standard error, to estimate how good our sample mean is, and we use standard deviation to describe the distribution or the scatter of our data. So there's one other thing that we can do with this sampling distribution. So again, hypothetically, if you have many independent samples from the population, the sampling distribution of the means here, which is this histogram of data, follows something called a normal distribution. And I've used this term in class, and I've been talking to you occasionally, but this is, I think, the first time that we're introducing it in the videos. So the normal distribution, also called a Gaussian distribution, has this classic bell shape, or this bell curve shape, which is what you see in the histogram here. It's a very widespread and useful probability distribution, and it'll feature prominently in later videos, as we'll talk about it more. The normal distribution is a continuous probability distribution described by two parameters. It has a mean and it has a standard deviation. I won't go into a lot more details about it right now, but it does have one extremely useful feature. Regardless of the shape of the normal distribution, regardless of its mean or its standard deviation, the same amount of data always occurs under a given area of the curve. So about 2/3 or 68.3% of your observations will be within plus or minus 1 standard deviation of the mean. About 95% or so will be within plus or minus 2 standard deviations, and about 99.7% will be within plus or minus 3 standard deviations. So remember that the sampling distribution of means, if we had randomly chosen a whole bunch of samples from the population and calculated the mean of each one, follows a normal distribution. So what that means is that about 2/3 of the means will fall within 1 standard deviation of the population mean on this sampling distribution, 95% within 2, and so forth. So the standard deviation of this sampling distribution is the same thing as the standard error of the mean. So that means that 68.3% of sample means should fall within 1 standard error of the true population mean. And you can calculate population mean from, or you can calculate standard error, from the standard deviation sample size of your data. About 95% of the sample means should fall within 2 standard errors of the population mean, and so forth. So this is the basis of something called a confidence interval. You can calculate any confidence interval. You can calculate a 50%, a 75%, but the standard concept is a 95% confidence interval. And so if the data follows a normal distribution, 95% of the sample means would fall within 1.96, slightly less than 2, standard errors of the true population mean. So this is a 95% confidence interval. So we would often just we would calculate a sample mean and then the 95% confidence interval on that sample mean. So the correct way to interpret a confidence interval is this. So if you took many random samples from the population, like we hypothetically did to generate our sampling distribution in previous slides, 95% of the confidence intervals on those means would include the true population parameter, which is in this case is the population mean mu. So here's how confidence intervals are used in practice. Imagine that we calculate a mean value of 1 per mil or part per thousand for, say, carbon isotopes in seawater in the Atlantic Ocean. Given the data that we have, we can calculate the standard error because we know the standard deviation and the sample size, and we can then calculate the 95% confidence interval on that sample mean. And it tells us it's between 0.3 and 1.6 parts per million, or parts per thousand. Let's say we also measure a bunch of samples from the Pacific Ocean, and we measure their carbon isotopes, and we calculate their carbon isotope composition as 0.15 per mil. Well, you'll notice that the sample mean for the Pacific falls outside of the 95% confidence interval for the Atlantic data. And so because of that, it's unlikely that the two groups come from the same population, and we can infer a significant difference between the carbon isotope composition in the different oceans. So basically, we would say this is not likely. If they came from the same population, our 95% confidence interval on that sample mean at least is 0.3 to 1.6, so they're probably not the same. So in R, standard error, there's no built-in function for it. It's very easy to calculate because there are 2 functions, one of which you know already. So remember, standard error is just standard deviation divided by the square root of sample size. So you've already seen the function for standard deviation, but you need to know the sample size. And so the R function, called length here, counts the number of elements or items in a vector. And remember, that vector can be a column in a data frame or in a subset. So that's how you can calculate sample size of a variable. So there is one complication if your data contains missing values. You've learned how with mean or standard deviation, you can use na.rm to remove the na values if there is missing data. However, length unfortunately does not have that option. So you will need to use a separate function this function called na.omit, on your numeric vector to remove any NA values if you want. So you got to be really careful about this, because if you remove the NAs when you calculate the standard deviation, you also have to make sure to do the same thing with the length. So we'll practice this and interpreting confidence intervals more in class as you're working through the programming part of things.